Okay, hello everyone. So today is Saturday. Let's study a paper, LIMU-BERT Unleashing the Potential of Unlabeled Data for IMU Sensing Applications, published by Xu Huatao, Zhou Pengfei, Tang Rui, Li Mo, and Shen Guobin. This figure actually summarizes the main contribution of this paper, in which the authors divide learning phases into two. So the first one is a self-supervised learning phase, and the second one is the supervised learning phase. So let's go into the details. Before that, one thing I would like to mention is that this paper actually won the best paper runner-up in Census 2021. Whereas Census is more like a sensor and system conference, but what this paper uses is actually a learning-based method, mainly inspired from the self-supervised learning from NLP. So, which is pretty interesting. Which means that the conference in system also favors ideas from other domains, which is in learning-based domain. So what's the challenge here? The first one would be label data are very scarce. So we actually want to, so this was actually in the context of all the data we have. So it's like everyone, every day, people are holding their phones and they can log their or captures many data from their mobile phones, but usually they are unlabeled, and it wasn't until someone actually collect them and also use them for in self-supervised learning that they would have someone to annotate some labels in those phone data. And the ratio of those label data over all the data we can capture is pretty low. So so that's why label data are scarce. If we can use if we use supervised learning, that would be a pretty strong signals to train a model, which is good, but the fact that label data are scarce. The second one would be the diversity in mobile devices and usage patterns and environments. So in mobile devices, so the paper is actually apply the map and test the methods in 4 datasets, including HAR, UCI, and motion sense, and also SHOAP. In here, I show these 6 figures, actually the screen snapshot of dataset from our group, which is not in the paper, but I would like to mention that you can search the keywords Wi-Fi, VI-FI in papers with code.com. The point is that it's pretty diverse, and we actually label those data, and it took us, I think it took like 5 or 6 persons and for a few weeks in order to label this data set. The second one would be the here this figure from motion transformer. Thinks that for the same walking pattern, so people, this person is walking, but if you would put the phone in different positions, what they call domain. So like in when this person is holding this phone, or when you put it in the pocket in the pants, or when this person is holding it in the bag, or just putting it in the trolley or in the cart, we can see it behaves very dramatically different. Differently. So this is one of the challenges here. Then this one I'm just trying to say that, I mean, unlabeled data are like everywhere. There's millions of unlabeled data in films. So can we use this? So the contributions of this paper are as follows. First, so well, in order to use millions of unlabeled data, and in machine learning, in deep learning communities, so people use a self-supervised approach to learn to general representation from unlabeled IMU data approaches to, and then so know that this is just general representation, and based on which some task-specific models can be trained with few labeled samples. And the third one would be that then the model is lightweight, so they use transformer. I will go into more details. Since transformer user is pretty has very high large number of parameters, and since they use it in phone domain, which there's obviously some hardware constraint. You can put a RTX and like 2080 or 3070 Ti put in a pocket. It's actually, the GPU is larger than the phone, but my point is that we don't have much computational resources. So this paper proposes a series of adaptations and enhancements around BERT to best work with IMU data in mobile sensing applications. And here is the main method in the first phase, which is self-supervised learning phase. They have LIMU-BERT. L stands for light. LIMU light, IMU-BERT. This is actually a transformer architecture, and then so it's denoted in purple and purpose. And here are the general representations and put into decoder. So this one is actually the self-supervised learning is actually done by math and reconstruction. So they mask some portions of the IMU data, and the model has to learn to predict those data. That's why they can learn to generate these representation. And the second phase is so know that a general representation actually just some representation. There's no direct correspondence between these representations and some task-specific things. By task-specific, I meant you can define, let's say we define a task as human activity recognition, right? That is actually a classification problem in machine learning, where we feed a sample of IMU and then we generate those general representations, and then we feed them, and we want to classify these IMU data, and we put them into some categories, whether someone is like walking or sitting or just lying down and so forth. And that's the job for this task-specific network classification. Or you can do something else like regression if you want to infer some locations based on your LIMU data. If the locations are in continuous space, then you can define a regression network here. So, so to be concrete, in this paper, they do human activity recognition, which is supervised learn as a which is a classification in this supervised learning. So they do have the class labels in this one, but they use pretty few labels compared to the conventional supervised learning. So yeah, this one is general LIMU representation, and then based on which we can fix the weight in the LIMU-BERT, and then train a task specific, train a classifier basically. So here are some more examples. So you can do device placement classification. It's like when we feed some you feed some LIMU data, you're trying to find which where the device is placed, such as whether it's in your hand or in the pocket or in the bag and so forth. And you can do human and computer interaction and localization and tracking and so forth. Localization tracking is mainly for regression. So the benefit is that with these general representations, they use like pretty small portion of label data, such as 1%. So here they use for HAR, human activity recognition, and DPC, device placement classification. Then, so the first question is, well, okay, this is good. We want to learn this general representation, but what kind of general features do we want for LIMU? So to do that, they analyze the main thing for classification. Since like for human activity, for HAR or DPC, the main thing is distribution. So distribution of individual measurements. What does that mean? So why? Because so let's look at some raw data. Here, if someone stands still and put it in the bag, it looks like this for acceleration. By the way, what for our new features, what the use is acceleration, which is in 3D, which is the forces measured in 3D, and gyroscope, which measures the angular velocity and also the magnetometer readings. So this one is the orientation in 3D in the magnetic field. Then the second, so let's say, so A is walking. Sorry, A is standing still and put it in the bag, and it looks like this. And it's pretty intuitive because if someone's standing still, then there shouldn't be lots of vibrations, or we should expect to see the acceleration to be very flat, right? And similarly for magnetometer readings, because the person is not actually moving. And for the second one, for someone is walking, we can see lots of change in acceleration, and we can see some periodic features. Because when someone is walking, it's actually like there should be some periodic patterns when someone's walking. A magnetometer look like this because it represents some orientation, whether someone is walking straight or turning left or right, and this thing can be captured in these three features. And the second one is when someone's put it in a pocket and someone's walking, If someone is surrounding, we can see much higher. We see acceleration in gyroscope or even magnetometer in higher frequency domain than walking and then stand still, which is intuitive because in a short-term period, the left and right legs I mean when someone's running, it means that the vibration of the phone it would be in a shortened cycle, and which results in higher frequency in the vibration than walking in B and C. So this is the first glance at the raw data. What we can observe is that if we are trying to classify the human activity, such as standing still, walk, and run, then we see the distribution are very different for those three activities. So we want the general features to learn those distributions. And second, if we see, let's check the back pocket and so in the back and in the pocket, we can see if it's in the back, we can see the magnetometer. It's more constant. I know it's not actually constant all the time, but it's more like somehow constant. The jitter is not that much compared to magnetometer readings in C, which is also working, but in a different device, different placement, which is in pocket. So we see more like vibration in X and Y axes, which can be used to classify whether the phone is placed in bag or in pocket. So this is what we want, the distributions of those features. And the second one is the temporal relations in continuous measurements. By temporal relation it means that in the time axis, how this data relates to the data in the maybe next few or future frames or next window or future windows and so forth. So we want to conclude, we want our general features to capture distribution and temporal relations. Before that, there's one big issue in BERT. So the main idea actually borrows from BERT, which is in NLP. If someone's in, I think it would be great to in order to understand this paper, it's great to first understand the technique used in BERT in NLP. But if you haven't read it, let me summarize. The main thing here is that they use bidirectional way to learn the general representation in NLP. So here, let's say we replace text with LIMU features, which is something like this, and we apply this method. Okay. So originally, the BERT does not consider normalization issues because why? Because the data are well normalized features. They are in one-hot vectors. They are in the imagined space like text. But in here, it's actually so here features in LIMU are not normalized. And which can cause lots of problems in machine learning because so one thing would cause the unstable chaining. So to alleviate this problem, the authors propose they actually try some different normalizations such as min-max, mean variance, Fourier transformation in deep sense, but they lose distribution information. So the proposal is to use this normalization. So basically, acceleration divided by gravity and magnetometer readings are normalized in among some magnetometer readings itself, so that the values will be more like consistent within some range. So alpha is just some scaling factor, some scaling factor. So here, let's introduce some notations. X is the data. So we have in as dim. So dim is 6 if we only have acceleration and just your readings, and else the length. So here we have unlabeled samples in U, denoted in U, labeled samples denoted in L, and also I correspond a true label. So here X label sample, so sample X, label is L, sample X of I in I instance correspond to true label in Y I. And then extending LIMU dimensions. So as team is very small, only 6. So they do some projections into a projected space which has a higher dimensions. So each team is the hidden dimension larger than S team. And then they use I, which is H by L, as the fused features in one column. And I contains more implicit features than normalized sensor data. And here's the main architecture. This is based on a transformer-based architecture. So I'm not going to details of transformer, and I believe there are many great tutorials for transformer. So the main thing here I would like to say is that they have different components. Here is the transformer-based architecture, and then you have decoder, and the training actually starts at the bottom right here. Let's go into more details. So first, in the self-supervised learning phase, they first map some subsequences. This one it follows so there's one trend of self-supervised learning method, which is by masking and reconstruction. There's another there are many other different kinds of self-supervised methods, such as contrast loss, but this one is meant for mask and reconstruction. So first step is to map some subsequences. Here we normalize data, and by the way we just mentioned, and then they do some span masking. Span masking I will introduce later, but it's here what we should know here is that they do some masking here, which is denoted in gray, in darker colors. So and then we project. So here is in a esteemed, which is like only 6 or 9 if we include a magnetometer readings. But the point is that 6 would be pretty low in low dimension. So we project it to a higher dimensional space, which is controlled by each team. Then here we would like to. We want the model to learn more implicit features in this higher dimension, and then we put it in the standard norm and positional encoding in transformer, and put in null, and then we put it into the transformer encoder. There's actually many different blocks here, which is denoted in RNum. Which is not the main interest in this paper, so I put it in transformer encoder. If you want to learn the details, just go to the transformer paper. and then the transformer encoder outputs the representation in HD. This is the main thing we want to learn, and then project to put it into decoder. The main thing for decoder is mainly to predict or reconstruct those data compared to the mass data. So we have so this is the task here for self-supervised. To summarize, we input mass data into the transformer encoder, and then we predict the reconstruct the whole sequences of LIMU data here. And then while the training is done, we use MSE loss in order to train, basically to minimize the difference between the reconstructed, so the difference in those mass data. We want so we have predicted reconstruct. So we have the reconstructed mass data, and we have the ground truth of mass data, which is we don't need to label because it's already in the data. And then we use a mean square error to minimize the differences between these two, so that the transformer is able to learn to reconstruct this mass data. Why? Before, let's go. So the main intuition is basically because the thing here is that we want to learn the context. We want to learn the distribution and temporal relation by masking. In order to do well in this job of reconstruction, well, the transformer encoder has to understand well in terms of the context, in terms of distribution, in terms of the temporal relation. So by doing this test, the transformer, we want the transformer to learn the context so that it outputs the representation, which is capture some very some impressive features that can be used for downstream tests. Okay, and then so before that, let's go back to the BERT transformer in the original BERT paper in NLP. The features to self-supervised tests. The first one is masked language model, MLM. To be specific, the randomly masked part of the input text and the model is trained to predict the original identity numbers of the masked words. Next one will be this next sentence prediction, NSP, which requires the model to determine whether the two given sentences are subsequent or not. Is it appropriate to use it directly in LIMU? Well, the first one makes sense because which is actually what this one does here. So they mask some parts of the input IMU, and the model is trained to predict. So mask some parts of here, and the model is trying to predict this mask data. And then the second one is not suitable for LIMU because of the frequent transitions. What does that mean? So know that we want to learn the context, the relation, when designing this test. So there should be some relation between this in LP, in text. There should be some relation between the current text, the current sentence, and next sentence. Let's see. Do I have some examples? No yet. But anyway. You can pick some text on, let's just put some Wikipedia and Wikipedia. But let's go to BERT. Just pick some example. So we introduced a new language representation model, which stands for bidirectional encoder representation for transformers. So let's say if I so if I pick some like this one and this one, that for the test for NSP test, well, this one has is the next sentence of this sentence. But sorry, which one did I pick? I think this one. Let's say this one. But this one is then is this one more related to the sentence, or is this sentence more related to the sentence? Well, if we look at the context, so here in this sentence we say there's some bird, and here is more it's like expanding the meaning of this one. So this is there's some relation between this one, some words which is birds, and between this sentence and the sentence. But if we look at this one, it's hard to find some direct relation. I think there could be some relation, sort of like in general, but it's not that strong of this one. Why this one helps? Because in order to do well in this test, the model has to understand the context, the relation between the sentence of two. Okay, let's go back to LIMU. But why this is not suitable for LIMU? Because frequent transition, to my best knowledge, is like when someone is walking and then suddenly he just runs. So if we are trying to predict whether some next window, whether it's walking or running, does it make sense? Well, do we actually have a relation between the walking and running? Well, the direct answer would be no, because walking and running just two activities. It could be due to some other factors in when someone is doing some activities, but there's no like direct relation. Someone can just stand still and then and then he runs in the next window. And then if we are trying to predict the relation between these two windows by next sentence prediction, it doesn't make sense. There's nothing we can learn. So that's why the authors conclude that we don't need to use NSP here. We only use MLM. Okay, math language model. I actually already introduced this method previously. The issue is that if we mask one token in BERT, in BERT they mask one token, but here we mask sentence is too short for LIMU. The issue is that if this is too short, seems like here is too short, the models can learn just by mirroring without learning anything. Because if you look at this this accelerations, when someone is walking, there are some periodic patterns here, and since this is periodic, we can just look at some windows left or right, and just copy it directly into the math portion, and without learning anything. So that could be one issue. So the authors propose to mask long sequence. To do that, the next question would be, how long should we mask the new sequences? So they use span and masking I just introduced. So now let's look at the more details. So basically, we sample the length of the new sequence to mask follows the geometric distribution. Like here, this one just is basically how we do the span masking. So let's go to this figure directly. I think it's more intuitive. This figure is actually from this paper, but I put it for illustration. You see this number of words, but here we want to understand LIMU sequence, the length of LIMU sequence. So basically, we have some probability distribution for different length, and that it looks like this. This is the distribution, and then we sample the we sample length, and in order to match, basically that's it. So the main thing here is that we have more portions in less in the mass sequence length and in shorter, but also we have some chance to mass long sequences. So then let's go to the lightweight model. So our original BERT is pretty large. The max sequence length is 512. So the window then is 6 seconds in their case. So the proposal is that we turn the dam sample features from 100 Hz to 20 Hz and have small hidden features, and they use cross-layer parameters, which means that the parameters of first layer is shared with other layers. And then they use, so after training and then the in the first self-supervised learning phase, and then they use only 1% of label data to train the model in the supervised learning. They also try different kinds of classifier. The first one would be just so we feed these general representation into GRU and drop out and fully connected layers to in the softmax to output the labels for a classifier. They also try multi-head attention and some 2D convolution for some alternatives. The sliding windows to do classification. So they do this one in different data sets. So some activity 6 or 7 activity and users 9 to 30, 24, 10, and so forth. And they compare it to these models. You can go to details, and we can see that LIMU-BERT and so the LIMU for general representation learning and GRU for classification use the best results in terms of accuracy and F1 with only 1% data label data. And then we can see some accuracy comparison at different label rates, ranging from 0.2 to 10%. And still, LIMU-BERT, also LIMU-GRU, use the best result in the first, in denoted in green. And some accuracy on HAR with different sequence length as well. And also performance on device placement classification. And one thing to see is actually the representation learned from LIMU-BERT, and they put it here. If the features are cluster-like, then it would be a very good. So this one, these are visualized in t-SNE, and if the features are in cluster-like, behave like some cluster-like things, it would be pretty easy for a classifier to learn, because so based on these features, what a classifier does learn, it learns is mainly the class boundary, right? If the features are already in clusters, then the classifier pretty much is just needs to like draw some boundary in even just in low in not too high dimensions. If the on the contrary, if they're not like this, if they scatter around for different classes, then it would introduce more difficulty for the classifier to do classification, because it also needs more complicated learning some layers in order to put it into some higher, such as in higher dimensional space, or some or introduce some nonlinear functions in order to learn the boundaries. But in short, it's good to see those clusters in the general representation. And here they try different classifier, and this one, GRU, is the best for this test. So among these classifier. And they also do some ablation study on features. So in short, using acceleration gyroscope, the combination of these both are the best, and the uses of magnetometer is that does not contribute too much for F1 score. And they also have some comparison normalization. So LIMU-BERT is better for among these. And mean vary use pretty low score. Okay, well, I'm just trying to understand why. But let me look at the details. Then to do this one, accuracy across data sets. So here's like when we change some data in one data set, such as HAR, but we want to do it in another data set, in the target data set, such as UCI or motion, how they perform, surprisingly, is pretty high. And also some ablation study on mass length. Sorry, some probability, span mass probability, P. Single mask. I think it's just one token, to my best knowledge. We also try different dimension, and 74, this one's a H. 74 is the best result. Here, I think it might be better to, well, anyway, I'm saying the colors. So the number of parameters is only in KB compared to original BERT, which is 110 million. Okay, so that's what we learned. We learned the general representation from unable data in self-supervised learning manner, similar to BERT, and also it's lightweight on mobile devices. Thank you.